a week from today, we'll talk about computing pi, different ways people have done it historically. You'll find there's more to it than you might think. And then a week from tomorrow, you can either come and take the final and be done with it if you like, and if you don't like, you can stay away and come the next week and take it. Oh, and one last thing then is that the fifth, let's see, no, not the fifth, the 29th is the last day for homework. So, end of next week. You don't plan to come on the 29th, then it would be the 28th, obviously. And I'm hoping to get them either today or tomorrow from you. And everybody should have a copy of the take-home part of the final. And okay. Uses, and so naturally you wonder what it is if you are looking at Maple. So if you ask Maple for a Taylor series and give it a command like this, say you define a function as 1 over 1 plus x, which is the sum actually of a alternating geometric series, as we have seen, you might type something like this. Series, you can either type series or you can type Taylor, either way. Then the function, which if you've already defined it, you can say f of x, or if you haven't defined it, you could put the expression here, 1 over 1 plus x, and then comma, and then powers of x minus 0 is what you mean. In other words, just powers of x. If you write x equals 0, if you wrote x equal 1/2, say, then it would come out in powers of x minus 1/2, and so on. And then you have a comma and then a number. So that number that the command requires does two things. It tells how many terms altogether are in the polynomial that you get, your Taylor polynomial. So the degree of the polynomial is this number minus 1, always. And you notice that because your constant is like starting with x equals 0, you get your 6 terms going through x fifth, and then this number appears as a power in this symbol, which is a large letter O, called big O, if you're saying it in words, of x to whatever number here is whatever number is there. So what I'm talking about first this morning is how you interpret this symbol, which relates to the error formula or the remainder formula. If you have a function that's not exactly a polynomial, then the Taylor series, or Maclaurin series in this case, gives you a polynomial and then a remainder, which is to represent the difference between what the polynomial would give you and what the true function value would be. The only time that this would not be present is if your function were a polynomial to start with. Then it would be, its own Taylor series would be a polynomial of that same degree, and then you wouldn't have any error. But for sine and cosine and so on, you do. When you say the polynomial value is the sine value or cosine value or log value, whatever it is. So the handout that you have, that's the copy of the book, which is in chapter 7, that defines the symbols little big O and little o. And as they would print, the difference would be in the size of the circle there. If you look at how they're printed in the book, you can see how big O looks and how little o looks in print. So, definition then, a function has order smaller, function f has order smaller than function g, or is of smaller order than g, or is of order smaller than g, any way you want to say it, as x becomes infinite when the limit of the quotient is 0. So if you can, for example, set it up as a L'Hopital rule limit as x goes to infinity of a function that you want to show is little o of another function g, has smaller order, you have that if your limit will be 0, which you might be able to get if your form is infinity over infinity, say, by doing successive derivatives or using some other limit theorem. So, for example, log x is little o of x because this limit, which you see is infinity over infinity, if you do the derivatives, is this limit from the log 1 over x, this limit's 1, and then your limit of 1 over x is 0, because 0 is a horizontal asymptote. Or you could say x squared is little o of x cubed plus 1. Notice this polynomial has higher degree than that. So again, the limit, if you set it up as a L'Hopital rule limit, you could either do a couple of derivatives and take the limit and get 0, or you could divide top and bottom by the highest power here, by x cubed, and see that your limit is 0 that way. If you divide it by x cubed, this would become 1 over x, and this would be 1 plus 1 over x cubed, and you get zeros. We also have big O symbols, which are the symbols that Maple uses. And so if you assume your functions f and g are positive for all x from some point on, and so the k then is could be any real number that's large enough so you could say these are positive once you're past that. Then you'd say f has at most the order of g, whereas here you're saying f has smaller order. Smaller order means the limit of the quotient will be 0. When you say at most g, then that does not require the limit to be 0, but simply that you can show that the quotient will stay bounded by some positive number, but it wouldn't necessarily have to settle down to be a limit. So something like sine or cosine, as x goes to infinity, you can't say a single answer for limit x goes to infinity of sine x, because sine of infinity is not a number, and isn't infinite either, because sine and cosine, by definition, have to stay between -1 and 1, because you go back to the definition of as ratios of sides of a triangle, for example. So something like that, you see there's an M because the absolute value, say, of sine is less than or equal to 1, but there isn't a limit, single number or symbol. And so you write f is big O of g when this quotient will stay less than some positive number, but not necessarily be 0 or 2 or whatever. So we read this as f is big O of g. Little o then, f grows more slowly than g, and big O, f grows no faster than g. So if the relationship is little o, then there is a limit, which will be 0, whereas if the relationship is big O, you do not necessarily have a limit. You may have, but you don't necessarily. You just know that the quotient remains bounded. So, for example, x plus sine x is big O of x, because if you set up your quotient and divide the x into that one, so it's also the same as this, you know that sine x over x will stay less than 1 in size, because the sine is, and then as x becomes larger and larger, whatever this is being divided by ever larger quotient. So you can certainly say that the original here is less than or equal to 2, because the most that sine x over x can be is 1, and the most that this can be is 1. So you're not saying that you have a limit, but you're saying that the quotient's bounded. And if you have a thing like this, e to the x plus x squared is big O of e to the x. Again, if you set up your quotient, if you actually do your limit, you see you're going to have 1 plus limit of x squared over e to the x, which is 0. So this one actually approaches a limit, which is 1, but which is to say that this is also little o. If something is little o, if the left-hand side is little o of the function on the right-hand side, it's also big O, because if it does approach a limit, then you can also say the quotient is bounded. But you can't go the other way around. So this is also little o of e to the x, and also always, if f is little o of g, then it's also big O, but you can't turn it the other way. So I gave you the copy from the book so that you would see how the print looks, and then I have the what is in my handwriting, which is essentially what's here.
Yeah, it does.
This is for that. Well, I'm just going to do it. Well, all right. If you're determined to.
Store the functions.
Oh, yeah.
And,
So you store the function, then execute another.
You can, but I don't think you need to do a
Oh.
series.
You mean in Maple?
In Maple, yeah.
Yeah.
Come back to our application of the big O idea. If you look at what is the remainder theorem for Taylor's series in powers of x minus a, then you focus on a particular x value, say x equals b, say that you want to compute your function by using a Taylor series at some value x equal b. So f of b is, and what you're using is the number a to evaluate your function and all the derivatives. So the a, if you were thinking of getting the Taylor series for sine or cosine, requires a value where you know exact values, if possible, so that you don't have any round-off error. So, for example, the one that we will work with over there under the clock is sine of 31 degrees. So your A would be 30 degrees because sine and cosine have exact values at 30 degrees, pi over 6. Then in radians, being 30 degrees, the sine is 1/2 and the cosines are at 3 over 2, which are exact. So typically, the A is something like pi over 6 if you were thinking of sine of an angle that's near 30 degrees. The B would be the actual angle for which you want a decimal to put in your table if you're back in the 1700s building the tables for the trig functions by hand. And that's then the math books all had tables in the back of the book until the 1970s and the development of the student scientific calculators. These calculators that you can buy for something like $10 now that'll do the trig tables and log and so on, came out. The first ones were out in the 1970s, and they were very expensive. I think that the first ones that we had at Boise State were made by Hewlett-Packard, and they were just a student scientific calculator. They weren't graphing calculators. And I was the math department chair at the time, so we bought 2 of them for the math department. These HP, I think the model number was 45, and they were $500. And the tuition at Boise State at that time was about $100. So $500, you could almost go to college there for the semester. I mean, as far as books and tuition, you could. So it was a lot of money. Well, this, of course, is Moore's Law and the price of computing power and how much you get, and it's certainly been true. But the point is that people used these tables originally done by this sort of thing by hand for literally hundreds of years. And certainly when I went to school, that's what it was. And the table was in the back of the book and so on. Well, anyhow, the nth Taylor polynomial would be something like this, which will have a degree n, and then the remainder will have degree on the derivative n plus 1. You evaluate this next derivative at some point in between a and b, and unfortunately, you never know exactly where. If you could do that, then you could get an exact value here, and you'd be essentially getting something for nothing. You'd be getting what is an infinite series with just a finite number of terms. So the best you ever can do with this is to try and say, well, the magnitude of the derivative cannot be larger than something, and get a ballpark on your error. And then you have x minus a, n plus first power. This number is going to be, in Maple, it's going to be like 6 if it were a thing where you're using this polynomial and then O of x6, for instance. And then whatever this number is and the order derivative, that number factorial is in the bottom. This is the form of the remainder and essentially the error term for Taylor series due to the French mathematician Lagrange. And I didn't write his name. Let's see where. Okay. And this is, I think, the most useful form of the remainder theorem. So the place where the value of the n plus first derivative would be taken for this to be exact could either be between A, where you're evaluating your derivatives, and the B, where you have the value that you want to put in your table, if the B is larger, or it could be the other way around if the B is smaller. In other words, if you were talking sine of 31 degrees and working with powers of x minus pi over 6, which would be like 30 degrees, then the C would be between 30 and 31 degrees. But if you were using the series to do sine of 29 degrees, the 29 degrees is less than the A, which is 30 degrees, and then you'd have it the other way around. The B is less than the C is less than A. So we don't know an exact value for C, but we can work to find an M where the maximum magnitude of the n plus first derivative will be less than or equal to M over the interval between where you're evaluating the sine, let's say 30 degrees, and where you're trying to get a number to put in your table, which might be 31 degrees or 32 or 29 or 28 or, of course, somewhere between. Well, for sine and cosine, things are especially nice because they're never bigger than 1 in size, and your derivative is never anything else except sine or cosine. So you can use capital M equal 1, and that's what we're going to do over there under the clock. Meanwhile, with the example with which we started, where we were talking about series for this, and if you wrote 6 in the Maple command, what you got was a polynomial of degree 5, which includes 6 terms, count them, and then the symbol O of x6. So then that goes back to the handout with the Maple, and there's probably some people who got here and didn't get this.
No, I think there's some.
You got that. Did you get this one? The Maple. If you notice what I did there, this goes back partly to what we were doing last week with the logarithm. First, I got the series for 1 over 1 plus x. Then I'm defining the corresponding Taylor polynomial as g. And then I'm integrating g. So term by term, that's line 4. And so line 5 then, you get the x minus a half x squared. So that's the series for the integral of 1 over 1 plus x, which of course is log of 1 plus x. So line 5 is the series for, well, it's the first 6 terms of the series for log of 1 plus x. And then I did the same thing over again with the series for 1 over 1 minus x and integrated. And so line 11 is the first 6 terms of the log of 1 over, the log of 1 minus x. And then I am adding, so log of 1 plus x plus minus log of 1 minus x. The difference of the logs is the log of the quotient. I'm down to line 13. So I have finally, if I add the series, line 14, the series for log of 1 plus x over 1 minus x. See, it has the odd powers of x. And we talked about this last week. I had a handwritten handout that was doing that. So then if you turn the page, you can see, if you're thinking about something like using log of 1 plus x over 1 minus x at x equal a third to compute log 2, you can see the fit between the Taylor polynomial and the actual log of 1 plus x over 1 minus x. And you see that between 0 and about a half anyway, your eye can't tell the difference in the two graphs. So you have a way to get at logarithms generally, and log 2 particularly if x is a third, that is reasonably efficient. And then I have the Taylor polynomials for various values, and you can compare the decimals with what your calculator would say for log 2. So then if you go on to the back side of the second sheet of paper, you see that I'm doing the same kind of thing for the side, which I've been talking about, going on with. So that brings us into getting the Taylor series appropriate for sine of 31 degrees. So 31 degrees is 31 pi over 180 degrees. Remember, you have to use radians because in calculus, it's always radians for trig functions because the derivative of sine is not cosine unless you're in radians. If it's in degrees, you've got pi, you've got a chain rule problem, you see. And so you've got pi over 180 degrees times cosine, every time you open your mouth. So that in a sense, that's what radians were invented to do, is to make simpler formulas. So anyway, it's 31 pi over 180, and that's 30 pi plus pi, and 30 pi over 180 is pi over 6. So what you want to do is evaluate sine and cosine at pi over 6, because you have exact values. So that's going to be the A, and then the B would be, if you want 31 degrees, the B minus A would then be pi over 180, which you notice is on the order of 1 over 60. It's a comparatively small number. To get fast convergence, meaning that you don't need very many terms of a Taylor polynomial, you want to have it so that the difference between the table value you're trying to compute and the exact value you have for the derivatives is as small a number as possible. So for example, with the log 2 computation, we used powers of x, in other words, powers of x minus 0. And then for log 2, if you're using 1 plus x over 1 minus x, your x is 1/3. So your value, the equivalent of b minus a in that computation is 1/3. Well, this one is more favorable. This is more like 1 over 60. And you see, the smaller that number is, the fewer terms you're going to need for a given level of precision, 5-place table, say, or something like that. When people were first doing the tables, they thought that a 4-place table was plenty good. And later on, people went to 5-place tables and so on. But anyway, what we would have then is sine of b, whatever it is, such as 31 degrees, is sine of a, whatever that is, such as 30 degrees, plus the derivative of sine at a, then b minus a over 1 factorial, and so on. So if you look at the sine, your pattern of derivatives is sine, cosine, minus cosine, then you repeat yourself. The derivative of this is back here, and so on. So this is the 0 order derivative, which is the function, then add 4, then next would be another 4, 8th derivative, and so on. So you only have 4 possibilities. And so your values are a half, or 3 over 2, or those numbers with minuses. Your coefficients can't be anything else, as I'm saying here. So your sine of 31 degrees, then, you see you have your f of a, or sine of 30 degrees, exact value. Then your derivative, cosine, exact value, x minus pi over 6, over 1 factorial, and so on and on, like that. And if you notice, with the red and green arrows, the coefficients are either a half, plus or minus, or root 3 over 2, plus or minus. And so the way to get this in summation form is to separate the reds from the greens, because with the reds you always have this common factor of a half and then a sign alternator. And you always have an x minus pi over 6 to some power, where the exponent will match the denominator number of the factorial. And these, where they're the red, you see this is the 0th derivative, first, second derivative, third, fourth derivative, fifth, sixth derivatives, so they're the even order derivatives. If you're thinking of 0, 2, 4, 6, like that. So you're going to have the even exponent on x minus pi over 6, and then that matches the number here with the factorial. And you see this, if you start with 0, first you go plus and then minus and so on. And to get this even, n goes 0, 1, 2, but 2n is always even. And then in the same way with the greens and the cosines, you always have the root 3 over 2. The sign alternator again, starting plus the first one, and then minus, and then plus, and then minus. And you always have an odd exponent. You see 1, 3, and the denominator matches. So as n goes 0, 1, 2, 3, 2n is even and 2n plus 1 is odd. So this gets the reds and that gets the greens, and then if you want to combine that, you can have your sign alternator and then the half, and with the x minus pi over 6 part, and the root 3 over 2 with the x minus pi over 6 part. So you can finally write it as a single series with summation notation. If you go through something like this, it's more tricky to write these series than it is to just write out what the pattern is. The people originally doing the computing only would need a pattern like this because they were going to use some Taylor polynomial, such as maybe going through the cube or the square, and call it plenty good enough. And if you look at the maple now, you can see that. Now, I guess that's where it is over here. So if you go back to the maple and say the line 32, which is on the start of what would be page 4, the back of the second sheet of paper there. So F is sine, and then I get maple to produce the series. You see, so 8 terms, so it goes through x minus pi over 6 to the 7. And then, as we said already, the big O means that essentially what big O is saying is that the error is less than or equal to some maximum value that your derivative could have, in the case of sine, between 30 and 31 degrees, and that derivative can't be more than 1 because it's either a sine or a cosine, and a sine and cosine are never more than 1. So that would be a 1 if you were talking about sine, and then it would be the x, which would be the 31 would be 1 degree in radians, so it would be pi over 180 here, and it would be this number, whatever, I had 8 for the sine example, so it would be this number to the 8th power over the, so the m here would be the maximum the derivative could have over then 8 factorial. See, the maximum back here with the logarithm would be the order derivative over that number factorial. So coming here, what we would have, well, I guess what I want is the maple. Okay, here it is. All right, so you look at down there at line 34, where I'm defining the function g as my Taylor polynomial that goes through degree 7, my 8-term Taylor polynomial. That unapply convert business is just a way to get Maple to define a function g, which will be the function that we've been working with. And you could just as well type g colon equal x arrow and then type in the function that you want. Does the same thing. So then my point is that you can plot the approximate polynomial that I'm calling f, and you can plot the actual sign, which, well, the sign is f and the polynomial is g. So if you look at the next page, you can't see the difference between about minus pi over 2 and pi over 2. You notice that there are really two curves there, but you can't tell which one's which because the polynomial is extremely accurate. So then, if you want to get some values, line 35, value the polynomial at 31 pi over 180. You see, Maple has put in the fractions, and then you simplify that, and you see the numbers there. So if you turn the page, anyway, what you can see, if you look at line 39, where I have h equals unapply, that's a polynomial now of degree 3. So 4 terms of the Taylor series, line 39. So if you plot that and the sign, you see that then you can begin to see a difference in the graphs. If you get below minus a half about and above 1 or something like that. And still the polynomial then of degree 3 is quite a good approximation. And then I have defined the function, and the next one is the quadratic, line 40. And if you compare line 40, that graph with the graph of the sign, you see you're still quite good between 0 and 1. So where the 0 is, where the origin is, that's an A. So because you're working with the differences from 30 degrees. So if you look at that picture going 0 to 1, that's really the interval between 30 degrees and 31 degrees, because 31 degrees is the 1 unit away from the 30. And so even there, your maximum error is very small. Now, better do this before I you to do in these problems in 10.9 is use some of the series for which we know the form, like the Maclaurin series for sine and cosine in each of the x, and so on. And then by substitution or by adding series together, that kind of thing, which you can do in the intersection of the intervals of convergence. They want you to produce series for other functions without doing all the derivatives. So for example, you know that the Maclaurin series for sine is, if you use a letter U, looks like this, and this is actually the interval of convergence is all values. It's minus infinity to infinity. You could prove that using the ratio test, for example. And so then if you look at problem 4, from this you can get the series for sine of pi over 2 times x, because you simply replace the u with pi over 2x, and then you notice what this is. There's a sine alternator, and the exponent is odd, so sine alternator, exponent on u then is on pi over 2x, the odd number, 2n plus 1, and the denominator number matches the exponent with a factorial. So it would start out like this. If you look at number 14, it wants the series for this function, sine of x minus these two terms. So f of x is sine x minus x plus x cubed over 3 factorial. So write your first terms of your sine series, and then subtract here. So minus x, 2 minus a plus x cubed over 3 factorial. And then you notice those cancel and those cancel. So you get this series. You get all of the sine series except the first two terms. Okay, number 24 wants the series for f of x where it's the product, sine cosine. So there are two ways you could go after this. One is to do what we call the quotient product, which is tomorrow's class, part of tomorrow's class, where you'd actually take the first few terms of the sine series and the first few terms of the cosine series and start multiplying them like you'd multiply polynomials. And what you'll get is the first few terms of the series that they want. The other way you can do it in this example is trig identity. 2 sine cosine is sine of 2x. So go back to here and use 2x for u, and then what you want is a half of the sine 2x series, which is what the book does. So you have the half because 2 sine cosine equals sine 2x. You have then 2x for u there and there and so on. And that's like what I did here. I'm taking 2x and raising it to an odd exponent and dividing by n plus 1 factorial. And then you can do you can play some games. You can take the half across the summation symbol. You can take a number across the capital sigma, the same as you can take a number across an integral sign, because the integral, after all, is a limit of a sum, and so the rules for what you can take across the integral sign match the rules for what you can take across the summation sign. So you can take this half inside, and then where you have a product all raised to the power, you can take each factor raised to that power. because you have matching powers, so you can take the 2 times the x, and this is the common power, and that gets you back to there. And then, if you take this, if you think of 1/2 as 2 to the minus 1 power, when you multiply, you add exponents, so 2 to the minus 1 times this, you have 2n plus 1 minus 1, so you have 2n. So it leaves you 2 to the 2n, the x to the 2n plus 1 over n plus 1 factorial. So that's kind of clever, but that's what they want. So problem 25 wants you to add series term by term. So if you have the intersection of 2 intervals where one series converges in interval I1 and the other one in I2, you can add the 2 series and say that series converges in the intersection. So for example, e to the x, the interval is all x. And 1 over 1 plus x, the interval is the open interval, minus 1 to 1. So inside, so the intersection of this with that is minus 1 to 1. So inside that, you can take the e to the x series and the 1 over 1 plus x series and add. So 1 and 1 are 2. Those are gone. Then you have x squared over 2 factorial plus x squared. This is a 2 and this is a 1 in the denominator. So you get 3/2 x squared. And then this one, this is a 6 and that's a minus 1. So you get minus 5/6. And then this is a 24 and a 1, so you get 25/24. So you actually have a pattern for this that you pick up over here. So the one, the e to the x series, you always have 1 over n factorial, and the 1 over 1 plus x series, your coefficient is either plus 1 or minus 1, because it's 1 minus x plus x squared minus x cubed, and so on. So if you recognize that, this is your formula for your coefficient. And you see, then you either have 1 over n factorial plus 1 or 1 over n factorial minus 1 as your coefficient. Okay, and then 26 wants cosine minus sine. And each of these is valid for all x. So your difference formula is valid for all x. So this is your cosine Maclaurin series. If you haven't noticed, there's a page in your book toward the end of chapter 10 that has Maclaurin series for common functions like that, all on one page. It's maybe in the section 10.10 or 10.11. It's in there toward the end of the chapter, you can find it. And anyway, here is your sine series, and you're going to subtract. So you notice I have a minus sign out in front. So if I bring this in, then I have minus plus, and then you notice these are even exponents and these are odd. So when I combine these are going to go in between the even terms. So you're going to get a thing that's like this. And the book leaves it at this point. You notice that you have a pattern. After you get started, you have 2 minuses, 2 pluses, 2 minuses, 2 pluses, and so Okay, so one last comment then on the remainder formula. You see what we're saying with the big O, if you were back to the example where we started, where you had the function 1 over 1 plus x, your actual remainder formula from Lagrange form, it would be the sixth derivative over 6 factorial x minus 0 to the sixth, because you're evaluating these derivatives at x equals 0 if you write it as a power series. Okay, so then what's O of x6 is really the Lagrange formula, meaning that that over x minus 0 to the sixth, which is the sixth derivative over 6 factorial, is some maximum number, some bound. The m then would be the most that the sixth derivative could be in the interval where you're working, divided by 6 factorial. And so that, even though you don't know exactly what value this is, to get this as a specific number, you can use something that would be the most this could be over 6 factorial. So then that says that the magnitude of your error is less than or equal to whatever is this maximum that this quotient could take times x minus a to the sixth. And so if you're working here with a number that's comparatively small, like pi over 180 for sine of 31 degrees, what you have is an m, which is the most the derivative could be, which is 1 for sine or cosine. You'd have the 6 factorial in the denominator and a number like pi over 180 to the 6th power, which is a small number. It's like 1/60th, 6th power, if this were the pi over 180. And then you're dividing that by 6 factorial, say, something of that kind. So that's why these polynomials usually don't have to be very high in power to get good values. 4 places, 5 places anyway. Okay, so the last day to turn in homework, for those of you who do written homework or want to do written homework to make up missing my math lab, would be week from today, 28th, or week from tomorrow if you come to class, which you may or may not do. So tomorrow we'll do binomial series, the last section in the chapter, Cauchy product limits. A week from today we'll talk about computing pi, and then a week from tomorrow you can come take the final if you want to take it early, be done with it. If you don't want to, don't show up, and you can come on May 5th, which is 2 weeks from today. And you have the big sheet of paper that says what the questions are about. However, they're not necessarily in that order. Okay. So any questions about what we're doing the rest of the semester? Well, come back tomorrow and hear about binomial series, and